This is a video on the pH scale. Before introducing the concept of the pH scale, I'd like to show you a simple, relatable analogy that I've been using over the years, and students get it. Suppose I give you a basket full of bags of lollies. Say I've got some sour worms, sweet boiled lollies, jelly beans, and boiled candies. Okay, I'll give you 4 bags of lollies, and then I'll then ask you to somehow categorize them. Now, one way you would go about this would be to place them along a continuum, a line, like this. So on one end of the line, you've got, let's say, the sweet lollies, and on the opposite side, you've got the sour lollies. And in the middle, you've got neither. Okay, you can also call that neutral. So for example, in this case, you've got the sour worms on the right. Let's put them here. You've got the sweet boiled lollies on the left. The jelly beans, you would place them sort of towards the left, depending on what type of jelly beans, of course. But for argument's sake, let's say they're sort of sweet, not too sweet, so they're sort of near the center. And in the middle, we've got the boiled candies. Okay, suppose they're neither sweet nor sour. Okay, that's a perfectly acceptable scale that you would use, and that's a good example of how you categorize something. Now, similarly in science, there's this scale called the pH scale, in chemistry, I should say. pH. It tells you basically how acidic or basic, and I'll talk about this in a sec, a substance is. Okay, it could be water, it could be Coke, it could be soap, just about anything. And pH is an acronym. It actually stands for power of hydrogen. Okay, pH. More accurately, it's a measure of the concentration, so the amount, in other words, the amount of hydrogen ions, H plus ions, in a substance. Okay, let me explain this briefly. Now, if you recall, an ion is a charged atom. Another way of saying charged atom. Hydrogen, if you recall, is a very simple element. It's the simplest element in the universe. Looks like this. So you've got 1 proton, okay, in the nucleus, and you've got 1 electron orbiting the nucleus. That's a typical hydrogen atom, a neutral hydrogen atom. Taking away the electron is the most favorable thing to do for hydrogen, okay, because when you take that away, it's now stable. Okay, it's happy. And you're left with a nucleus behind. Okay, 1 proton. So the H becomes H plus, superscript plus. The plus means, okay, you can write +1 as well. Tell my students that's fine, +1. The hydrogen has lost 1 electron to become positive, okay? You're reading it right to left. So that's how you get a hydrogen ion, okay, by simply removing an electron. So that's what a hydrogen ion is. Now the pH scale starts at 0 and ends at 14. Make it a bit bigger. Ends at 14, and it goes up in increments of 1. Okay, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, and these should be equally spaced. I'm a bit sloppy and lazy in this case, didn't do that. A pH of 7, so 7's in the middle of 0 and 14, that corresponds to a neutral substance. Okay, it's neither acidic, so acids have a pH from 0 all the way to 6. Bases from 8 to 14. So a pH of 0 would mean that you've got a very acidic acid. You would not want that to go anywhere near your skin. That will burn it like hell. Similarly, a base with a pH of 14, okay, the maximum pH you can have will also do the same thing to your skin. Things like bleach, toilet cleaner, all that sort of stuff, they're strong bases typically. That's why people wear gloves when they're cleaning their toilet, okay, because it will get into your skin and cause nasty stuff to happen. So that's it. It's very simple. It's basically a scale with numbers from 0 to 14. Tells you how acidic or basic a substance is. I like to use red for acids, but anyway. So 0 to 6 acids. Just think blue for 8 to 14 as bases, as being a base. Just a note here as well. Students get confused with this every time I teach it. Remember that the lower the pH, the more acidic something is. More acidic. Okay, the lower the number, so 0, for example, e.g. 0 is more acidic. So a substance with a pH of 0 is more acidic than a substance with pH 6. Another example, a substance with pH 8 is less acidic than a substance with a pH of, let's say, 4. And that's the idea. To put it another way, the higher concentration of hydrogen ions in a substance results in the substance being more acidic and the pH is lower, and vice versa. In other words, the lower the concentration of hydrogen ions, the less acidic and the pH is higher. Also, it turns out that as you go up or down by 1 value in pH, the substance becomes 10 times less or 10 times more acidic, respectively. Let me show you what I mean. If I go up in pH, okay, the substance is less acidic by a factor of 10. Each time you go up, you add on a times 10. I'll show what I mean in this case. A pH of 3 would be 10 times 10 times 10, which is 1,000 times less acidic than a pH substance with pH of 0. Okay, let's do some more examples here. So let me redraw the pH scale just partially. 1, 2, 3, 4, 5, 6. Suppose okay, let's do times 10 times. The idea is times 10, then times 100, then times 1,000. So the numbers tell you, basically, it's like a trick, how many zeros there are. Going up from 0 to 1, there's 1 0. Okay, going from 1 to 2, there's 2 zeros. To 3, there's 3 zeros, and so on and so forth. 1, 2, 3, 4. pH of 4 is 10,000 times less acidic than a pH of 0. pH of 2 is 100 times less acidic than a pH of 0, and so on and so forth. That's how it works. Examples of substances with different pHs as well, just a note. So stomach acid, hydrochloric acid in your stomach has a pH of around 1. Okay, typically 1, so it's very acidic. Lemon juice, pH of around 2. That's why it burns if you've got like a wound or something on your lips, and your lips are sort of dry. You feel that burning sensation. That's because it's quite acidic. Gets into your skin. Orange juice, pH of 3. Tomato juice, pH of 4. Things like black coffee. So coffee is actually slightly acidic. pH of 5. Your urine is also slightly acidic. So there are examples of acids. Here are some examples of bases. Let's go from 8. Remember, it's 8, not 7. 7 is pH neutral. So substance with a pH of 7 would be something like pure water. Okay, up from the mountains, let's say. So basic means 8, 9, 10, 11, 12, 13, 14. Let's use blue. pH of 8, something like seawater, slightly basic. Baking soda, pH of 9. Ammonia, pH of 11. So ammonia is actually used in household cleaning products. You want to wear gloves for that. Soapy water also, pH of 12. Bleach, pH of 13. It smells horrible as well. Not only is it bad for your skin, it's also bad for your lungs. It's an irritant for the lungs. And there you have it. That's the pH scale. A bit more into acids and bases. So acids, as I mentioned, like to release hydrogen ions in a solution. So if I plonk an acid in like water, let's say I've got a beaker here. I've got some water and I pour in some hydrochloric acid, which is HCl. The HCl, there's a fancy way of saying splitting up in science, in chemistry. It dissociates. Dissociates means to split. Now, a neutral substance like hydrochloric acid, as is the case with most compounds, are neutral. Okay, the HCl becomes H plus and Cl minus. Okay, why is that? Well, because remember the crisscross, the rules for combining elements into compounds. Stick them together, HCl, and you don't bring down anything because the +1 and the -1 stay as they are. That's the rule. So that's how you get HCl. So the HCl, when you pour it in, becomes a sea of H plus and C minuses floating around. Okay, so HCl is an acid. That's why you get H plus hydrogen ions. As for bases, they actually release what are known as hydroxide ions. And hydroxide ions are negatively charged. It's called the hydroxide ion. It's a polyatomic ion. Poly means many, atomic means atoms. So it's got more than one atom. So it's got made of oxygen and hydrogen atoms. And they release hydroxide ions in a solution. A good example of that is sodium hydroxide, NaOH. That's a base. Pour it into water and it dissociates into sodium, which has a charge of +1, and hydroxide, which has a charge of minus. Okay, plus and minus attract and they cancel out and they give you NaOH. Okay, so Na plus, OH minus, stick them together, you get this. Here's a memory device I've been using over the years with students, and I really like it. Ha, an acid, O, a base. H for hydrogen plus ion, O for hydroxide ion. Okay, very nice acronym there to know what ions go with what substance. Some practice questions for you to do. I want you to identify, so question 1, identify whether the following are acids or bases. Okay, very simple examples. H2SO4, so this is sulfuric acid. I've just told you the answer, but you've got to tell me why. So look at the ions, what it's made of. Sulfuric. You've got this carbonic substance. I'm not going to tell you what it is. I won't give it away in this case. C, suppose nitric HNO3. D, lithium hydroxide. E, potassium hydroxide. F, calcium hydroxide. It's question 1 there. Question 2. State whether the following are acids, bases, or neither. Okay, a pH equal to 3. B, pH equal to 5. C, pH equal to 7. D, pH equal to 10. So you can pause that and do them in your own time. I'm going to move on now onto indicators very briefly. So how do you actually determine if an acid is acidic, if a substance is acidic or basic in the lab? You use things called indicators. Indicators, as the name suggests, these are chemicals that change color when exposed to a substance. Okay, the most common textbook example is that of litmus paper. Litmus paper comes in strips, so sometimes you'll have like red litmus paper. It's all red. It's a light red, so I'm going to use the light red color. Okay, it's not really crimson. It's a light red. So it's just a strip like that. And red litmus paper, if you put that in an acid, it turns red. Okay, if you put it in a base, it turns blue. Now, litmus paper is great. It shows you qualitatively. So in terms of statements, in terms of no numbers, it just shows you what whether a substance is acidic or basic. It doesn't tell you the pH of a substance. That's where universal indicators come in. Okay, these are a mix of chemicals. These are more accurate, and contain multiple chemicals in one. Okay, multiple chemicals, more accurate, contain multiple chemicals in one, and give you the pH of a substance. Okay, they're more quantitative, they give you numbers. Examples are phenolphthalein. I hope no one asks you this in an exam because I can't even spell it at times. It's very, very difficult. Phenolphthalein. Things like bromothymol blue as well, another liquid. You can even use cabbage, red cabbage at times. But these are the most accurate forms of universal indicator, along with others. So that's it. That's pH, acid, and bases in a nutshell.